The Earth just got slapped by a 700,000 km/h solar wind stream, courtesy of a rare trans-equatorial coronal hole. This happened precisely as the interstellar comet 3I Atlas vanished behind the Sun without a peep. Experts are calling it a perfect coupling event. The magnetic gateway ripped wide open, ready to ignite geomagnetic storms with almost no resistance. At the same instant, a sudden surge in powerful earthquakes sparked a heated debate. Coincidence or cause? Some scientists immediately dismissed any connection. Others warned we were witnessing a cosmic pattern unfold. The official line? Nothing links these events. But 3I Atlas was doing something with our Sun, and when it reappears, what we find could rewrite the rules. The immediate question: what does a solar storm of this magnitude really mean for Earth? A coronal hole isn't a literal hole in the Sun. It's a region where the solar atmosphere thins, and the Sun's magnetic field lines stretch out into space, unanchored. Most of the Sun's surface traps hot plasma with tight, looping magnetic arcs. But inside a coronal hole, those lines open wide, like a gate left ajar, allowing charged particles to escape at extraordinary speeds. On satellite images, these areas appear as dark, yawning gaps, sometimes spanning thousands of kilometers and crossing solar hemispheres. When a coronal hole stretches across the Sun's equator, it becomes a trans-equatorial highway for solar wind, directly channeling energy toward the planets. The October 2025 event was captured by SOHO, revealing a vast unipolar coronal hole bridging the Sun's hemispheres. Magnetograms confirmed the field was negative and open, a rare configuration outside of solar minimum. This open structure allowed a high-speed stream, clocked at up to 700 km/s, to break free and rocket through the inner solar system. Space weather physicist Dr. Tamitha Skov describes these regions as magnetic exhaust vents, where the Sun's plasma doesn't just simmer, it surges outward, unchecked. The direction and polarity of this outflow are critical. When the Sun's open field aims directly at Earth, our planet's magnetic shield is forced to contend with a relentless, focused blast. This is the physical mechanism behind the perfect coupling setup. The magnetic door is open, the wind is fast, and Earth is directly in the path. What happens next depends entirely on how these fields interact. Solar wind doesn't just brush past Earth. When a high-speed stream arrives, especially one hitting 700 km/s, our planet's magnetic shield is forced into a direct contest. The real drama unfolds at the boundary where solar and terrestrial fields collide. Here, the interplanetary magnetic field IMF is key. In October 2025, the IMF pointed sharply southward, holding steady near 12 nanotesla. This orientation is critical because Earth's own field points north. Opposite directions mean the fields can snap together, a process called magnetic reconnection. This is the gateway through which solar energy enters the magnetosphere. These translate to real-world effects: power grid fluctuations, satellite drag, and most visibly, auroras stretching far beyond their usual haunts. On the night of October 12th, curtains of light rippled as far south as Michigan and Maine, a direct consequence of the efficient coupling between Sun and Earth. The result: a geomagnetic system primed for action where even a moderate solar wind can trigger a chain reaction across the planet's upper atmosphere. Each spike in velocity, each shift in polarity, sends a ripple through the global electrical environment, setting the stage for questions that reach well beyond the magnetosphere. 3I Atlas isn't just another icy wanderer. It's the third interstellar object ever confirmed, and its chemistry challenges everything we thought we knew about comets. Most comets in our solar system are dominated by water vapor. But 3I Atlas is different. Its coma is fueled by carbon dioxide, outgassing at rates nearly 8 times higher than water, a signature more typical of the frozen outskirts beyond Neptune than anything born in our own backyard. Spectroscopy from ground and space telescopes paints a picture of a nucleus smaller than a kilometer, yet active enough to shed material at a rate of up to 4 kilogaudases. Even at distances of 4 or 5 astronomical units from the Sun, it was already producing a visible coma, a cloud of gas and dust that forms when sunlight heats the nucleus. The dust itself tells another story. Instead of the fine grains that create long, glowing tails, 3I Atlas seems to favor larger, heavier particles. The result, a faint, asymmetric haze rather than a dramatic streamer. Its rotation period, just over 16 hours, matches the restless, tumbling motion seen in other active comets. But the details of its surface chemistry, rich in organics with a high carbon dioxide to water ratio, set it apart. As one SDO mission scientist put it, "This is a messenger from another star system carrying a recipe we've never tasted." The uniqueness of 3I Atlas isn't just a curiosity. It is a test case for how interstellar chemistry responds to the Sun's heat and what secrets might be revealed as it rounds perihelion. A cluster of magnitude 7 earthquakes rattled seismographs across the Pacific Rim, the same week that 3I Atlas disappeared behind the Sun and the solar wind battered Earth's magnetic field. The timing fueled a wave of online theories, some claiming the Sun's outburst or the comet's passage had triggered the seismic spike. Yet, when examined against the global baseline, the numbers tell a different story. According to NOAA's Space Weather Prediction Center, Earth averages around 15 magnitude 7 or higher quakes each year. This week's activity, while dramatic, falls well within statistical expectations. No mainstream seismologist accepts a direct physical link between solar wind and tectonic plates. Meta-analyses of decades of data find no reliable pattern connecting solar storms to earthquake timing. Still, speculation persists. Fringe theories invoke ionospheric coupling or subtle changes in Earth's rotation, but these remain unproven and outside accepted geophysics. As NOAA forecaster Michael Former explains, the burden of proof lies with those claiming a connection. Without a reproducible mechanism or clear statistical anomaly, science treats these events as coincidence, not causation. The debate isn't just academic. It sets the standard for what counts as evidence when extraordinary claims collide with data. 4 distinct outcomes await on the far side of the Sun. Each has a signature that reveals itself in the data before the comet itself comes into view. Number 1. Survival. 3I Atlas survives perihelion intact. The comet reappears with a brightness curve that matches pre-conjunction predictions, steady, perhaps faint, but unmistakably on track. Its coma remains compact, and no sudden changes ripple through its light. This is the outcome most comet scientists expect, but it's also the least dramatic. Number 2. Fragmentation. In this case, the story shifts instantly. Spacecraft coronagraphs, SOHO's LASCO C3, Stereo A Shy 1, Parker Solar Probe's WHISPER, would catch a sudden jump in brightness, often by more than a full magnitude. Instead of a single point, images might reveal a string of fragments, a train of nuclei stretching along the comet's path. The dust cloud expands, the coma blurs, and the tail may split or kink. Past cases like C2011 W3 Lovejoy and C2012 S1ISON showed these signs: abrupt brightening, bifurcated tails, and multiple points of light where only one belonged. A sodium tail, rare, bright, and yellow, can flare up in the wake of violent disruption captured in LASCO's sensitive filters. Number 3. Dormancy. The comet emerges, but its activity collapses. The coma shrinks, the tail fades, and the nucleus appears almost stellar. Faint, unresolved, and possibly lost in the solar glare. The brightness curve drops below forecast, and ground-based telescopes may struggle to recover the object at all. This outcome mimics what happened to several faint sun grazers. A return so quiet it's nearly invisible, with only a sharp-eyed instrument scientist flagging the anomaly in the data. Number 4. Disintegration. The most dramatic fate. The comet simply fails to reappear. No trace in coronagraphs, no fragments, no outburst. Just a silent gap where the nucleus should be. The only evidence is a ghostly dust trail or a brief, unanticipated spike in brightness as the nucleus vanishes. Each of these outcomes leaves a fingerprint in the data: a brightness jump, a sodium flare, a train of fragments, or a vanishing act. When the images drop, these are the signs to watch for. Recovery begins with a single image, SOHO Eslasco C3 coronagraph, uploading its latest frame to the Quick Look archive. Every 12 minutes, a new snapshot appears, and comet hunters around the world scrutinize each pixel for signs of 3I Atlas. The first hint could be a faint point of light, a sudden brightening, or a subtle distortion in the solar background. When the data stream shows anything unusual, an unexpected spike, a new fragment, a sodium flare, alerts ripple through the observing community. Robotic telescopes take over next. Facilities like the Zwicky Transient Facility and Pan-STARRS are programmed to sweep the region as soon as 3I Atlas moves far enough from the sun's glare. These telescopes cover enormous swaths of sky in a single exposure, capturing anything that stands out from the background stars. Each night, their automated routines compare fresh images against star catalogs, flagging any object that shifts position or changes brightness. If a candidate appears, photometry protocols kick in. Observers measure its light in multiple filters, logging the magnitude and color in real time. A steady, predictable rise supports the case for an intact comet. A sudden jump suggests fragmentation or outburst. Amateur astronomers play a critical role in this relay. With the right timing and a modest telescope, backyard observers can confirm or challenge early detections. Their images, uploaded within hours, add redundancy and extend the search into gaps between professional surveys. Every successful sighting is logged with precise coordinates and brightness, building a chain of evidence that tracks the comet's recovery. This coordinated approach, spacecraft triggers, robotic sweeps, and human vigilance, forms the backbone of the post-conjunction search. Every clear morning for the next 2 weeks, a comet waits in the east. Brighter than most city dwellers ever realize, yet easy to miss if you don't know where to look. Comet C2023A3, better known as Lemon, now glides through the constellation Cancer, rising before dawn and offering a rare chance for anyone with a pair of binoculars to catch a living piece of the solar system in motion. No telescope required. Just step outside an hour or two before sunrise. Find a spot with a clear view of the eastern horizon and scan just above the familiar stars of Cancer. Lemon's predicted magnitude hovers between 4 and 5, bright enough to stand out as a fuzzy, diffuse patch, but not so bright it leaps out to the naked eye. Under dark skies, the coma may look like a soft, round cloud with a hint of a tail stretching away from the sun. Timing matters. The next 14 mornings are peak, as Lemon climbs higher each day and the moon stays out of the way. By mid-November, the comet will fade and slip closer to the sun's glare, making this window the best shot for a first-time comet observer. A simple 7x50 or 10x50 binocular, anything you'd take to a ball game, will do the job. Even in suburban skies, the comet is visible if you know exactly where to look. Many amateur sky watchers keep a star chart handy or use a phone app to pinpoint its position. Some set alarms for 4:30 a.m., grab a thermos, and step into the backyard before the world wakes up. For those who catch it, Lemon is more than a smudge of light. It is a practice run for bigger cosmic events to come. A way to tune your eyes to faint details, learn the rhythm of the sky, and join a community that chases these fleeting visitors across the heavens. Long after Lemon fades from the morning sky, the calendar of cosmic events stays crowded. Another comet, C2026R2 Swan, is already drawing attention for reasons that go beyond simple brightness. In early 2026, Swan is expected to reach binocular visibility. But what sets it apart is the ultraviolet glow enveloping its head, a hydrogen corona first detected by the SWAN instrument aboard the European Space Agency SOHO spacecraft. By comparing the light curves of Swan and Lemon, how each comet brightens and fades over time, researchers can tease out the hidden physics that govern outgassing, fragmentation, and the slow erosion of icy bodies under solar heat. The sky's agenda doesn't end with comets. 5 milestone dates now stand out as waypoints for anyone tracking the solar system's restless pace. Late October, early November 2025, the recovery window for 3I Atlas, when telescopes worldwide will hunt for its return from behind the sun. April 13, 2029. Asteroid Apophis will pass so close to Earth that it will dip below the altitude of geostationary satellites, a flyby within 32,000 kilometers, visible to the naked eye over parts of Europe and Asia. September 20, 2040, a planetary alignment, when Mercury, Venus, Mars, Jupiter, and Saturn will all cluster on one side of the Sun. The year 2060, the possible arrival of a megacomet, flagged in current surveys as a distant, slow-moving object that could rival the great comets of the past. 2177. Pluto will complete its first full orbit since its discovery in 1930, a slow, stately lap that frames the entire modern era of planetary science. Each of these dates is more than a curiosity. They are reminders that the solar system is a living laboratory, constantly shifting, always offering new puzzles to solve. The sky calendar is open, and for anyone willing to look up, the list of appointments is only getting longer. In late September 2025, a trans-equatorial coronal hole unleashed a 700 km solar wind stream, driving geomagnetic storms and auroras as far south as Michigan. At the same time, interstellar comet 3I Atlas vanished behind the sun, its fate unknown until late October. While some noted a spike in magnitude 7 earthquakes, seismology records confirm that such clusters occur about 15 times per year, with no proven link to solar activity. Spacecraft including SOHO, Stereo, and Parker Solar Probe captured the critical conjunction window, but their data leaves open whether 3I Atlas survived, fragmented, or disintegrated. As of now, no classified files address the comet's outcome. What is certain is this: the interplay between solar physics, planetary defense, and citizen science is ongoing. The next chapter begins in late October, when ground telescopes will search for 3I Atlas's return. In the words of mission scientist Dr. Tamitha Skov, "The sun's story is written in data, not guesses."